what is the largest perfect square? And you want to pick the largest because it's just going to make your life a little bit more direct. Largest perfect square that goes into 500. Joe? 100. 25 goes in, but it's not the largest. So 100 would be the best. So you're pretty much thinking of this as root 100 times root 5. And then you actually can evaluate the square root of 100 without a calculator. That's just 10 root 5. Okie doke. And here, you can't simplify either of them as they stand right now. So we would first do the multiplication, and we'd get root 18x squared. So the largest perfect square that goes into 18, what do you got for me, Connor? 9. Root 9 times root 2. And then with variables, if you're looking for a square root, you're looking for the variable to be divisible by 2. If you're looking for a cubed root, you're looking for the variable's exponent to be divisible by 3, so on and so forth. So this one, we're actually just not going to touch because we're taking the square root, and that exponent is already divisible by 2. So if now that it's all split up, I can look at the pieces that I know how to evaluate. The square root of 9 is 3. The square root of x squared is x. And then root 2. We're going to come back to that one, believe it or not. A little asterisk next to that, because that is technically not correct, but I'm not ready to talk about it yet. That'll be one of our little adult moments where we're getting to a little bit of a nitty-gritty math here, and we got to think about special cases. But anyway, number 3, with a fraction, you sort of just kind of split it up. Root 100 over root 9, and that just gives us 10 over 3. And with 4, you actually it already is split up, but actually rather than simplifying the numerator, and you can't simplify the denominator, you'd have to leave it as root 6x. That would be an issue because you know that you're not supposed to leave a radical in the denominator, right? You would have to rationalize that. So actually sometimes here it was convenient to actually split it up. Here it's convenient to actually reconsider this as one full fraction because we can reduce that first and then only be dealing with one term. So then that would become 48 divided by 6 is 8. X cubed divided by x is x squared. And then we can now break this down. So I know I'm showing more steps than a lot of you do by doing the root 4 times root 2. And then again with the x squared, I don't have to touch it. And then the square root of 4 is just a whole number 2. Square root of x squared is just x. And then root 2. And again, I already have that one started. I'm going to come back to that as well. Hey, what do you know about adding radicals, John? Right, it's like combining like terms. We say combining like radicals. It's like fractions. You need a common denominator. Here you need a common radical in order to be able to add and subtract. You can multiply anything, right? We saw that. They don't have to be like radicals to multiply, just like with fractions. But with addition, you need them to be like radicals. So the first thing we would want to do is see if we can simplify either one of these. Obviously, the root 12 is the same thing as root 4, root 3. Which would just be 2 root 3, and then we have 9 root 3. And 12 divided by root 8. Now here are a couple things. You can simplify the radical 8 first. You're still going to have a radical in the denominator though. that you'll have to then rationalize. So you can simplify and then rationalize, or you can just rationalize first and then simplify. It doesn't really matter. Sometimes if you, let's think about this. Sometimes if you simplify first and then rationalize, you're just going to have to simplify again anyway. So because of that, rather than simplifying twice, sometimes I just like to get the rationalizing out of the way. So multiply by root 8 over root 8. And then I'll take care of the root 8 is just root 4, root 2. And then the square root of 4 is the whole number 2. So 12 times 2 up top is just 24 root 2 over 8, which is just 3 root 2. Olivia, can you remind me how to rationalize something like that? Yep, starts with a C. O N J conjugate. Yep, that's correct. So 5 minus root 3. And then, of course, you have to distribute. So up top, when you distribute your 7, you get 35 minus 7 times root 3 is just 7 root 3. The beauty of conjugates is that your outer and inner, when you FOIL, will cancel. So your first times your first, 5 times 5 is 25. Your outer, and I'm not going to write this down, your outer is minus 5 root 3. Your inner is plus 5 root 3. So again, that's the beauty of conjugates. That's why those radicals cancel. And then a positive root 3 times a negative root 3 is just a negative what? Positive root 3 times negative root 3. Andrew? Minus 3. Yep. So if at first you process negative root 9, you're not wrong. It's just that root 9 then becomes the whole number 3. And then we just make our denominator 22. Here's what not to do. 35 minus 7. You can't do that, because that 7 is not a whole number. It's 7 root 3. Any questions? Okay, in 8, what do you think our answer is here, Mackenzie? 4. Anybody think they might disagree with that? Andrew, what do you think it is? Right, the obvious other option is negative 4. Should we take a vote? If you think it's 4, I want you to hold up 1. If you think it's negative 4, I want you to hold up the number 2. So 4 is 1, negative 4 is 2. On your mark, get set, go. Hold them up, I can't see. Above your head. 1s, 2s. It's about split. It should be 4. Okay, and that's because of order of operations. But you guys have been conditioned from a young age just to see a square root and a square, and they cancel, right? And shortcuts are wonderful, but they also sometimes lead to little things like that. Not all shortcuts, but obviously this one. The order of operations here would be to simplify under the radical first, in which case that would become 16, and the square root of 16 is 4. So this is where we are going to have to go back to number 2 and number 4. Go down here, I put a little section for it. When you ever square this, or simplify the square root of x squared, it's not just x now, then, is it? Right? Most of you would tell me that this equals x, but that is not true. Because if it were true, then that should have been negative 4. Do you follow? Okay? The reality is, and it's because of, you can see the mechanics when you actually do a numerical example right there in number 8, the answer is that the square root of x squared is the absolute value of x. And it's a little stipulation, like a fine-tuning thing to perfect. Anytime your root is even, and you're taking an even root of an even number. Okay, so the 4th root of something to the 4th power would follow the same stipulation. The 6th root of something to the 6th power, and so on. That is always going to be the absolute value of x. And it protects against, by putting those absolute value signs there, it protects against this case right here. And you can kind of, again, I give you a numerical example so you can really concretely wrap your head around it. If it is odd, if it's the cubed root of something to the cube power, then it will just be x. If you think about like the cubed root of negative 3 to the 3rd, again, you would do negative 3 to the 3rd power first. It's negative 27. So when you take the cubed root of negative 27, you will get negative 3. So whatever x was is what x is in the odd case. It's the even on even that you have to worry about. Okie doke. So back to 2. When we simplified the square root of x squared, that needed an absolute value. Back in 4, when we took the square root of x squared, that also needed an absolute value. But I know you didn't know that, right? No one's ever seen that before in their life, right? So, there you have it. On number 9, we're just simplifying. So the square root of 54, biggest perfect square that goes into 54. Go ahead. 9, very good. What's your first name again? Marissa. 3 root 9 root 6. And the biggest perfect square into 24 is 4. So square root of 9 is the whole number 3 multiplied by the 3 that's already there. That's 9 root 6 minus square root of 4 is 2 times the 2 that's already there minus 4 root 6. And we get negative 5 root 6. Good stuff. Did I do something? Don't ask. Because I woke up 15 minutes late this morning and I'm off. Can I use that as an excuse all week long? All right, good. Thank you. 5 root 6. Sorry about that. Just a quick clarification. What's the difference between just when you're asked to evaluate the square root of 16 versus if you were asked to solve the equation x squared equals 16? What's the difference there? Oh boy. Mitch. Perfect. Exactly the point I wanted to make by just showing this. So anytime you're solving and you take the square root of both sides, you have to remember that the positive version is an option and also the negative. You have to insert that plus or minus. Reason being because that question is starting off as what squared could be 16. Positive 4 when you square it and multiply it by itself could be 16, and obviously negative 4 when you multiply it by itself, the double negative could become 16. Whereas when you're just flat out asked to evaluate what is the square root of 16, you are, in math, we inherently assume that you're asking for what is called the principal square root. So when we say that this equals 4, that's called the principal square root. Really just acknowledging that Yes, there is something else that multiplies by itself to get a 16, but the principal one always just kind of assumes they want the positive answer. So if you're evaluating, you're just giving the positive, but if you're in solving, you're going to, anytime you take that square root of both sides, plus or minus. Okie doke. Key vocab, we've got rationalizing, you know what that means, to get rid of the radical in the denominator, and then principal square root. Any questions? Okie doke. What's on the back? We jump up to fifth roots, fourth roots, third roots. So, you know, the higher, we obviously know maybe 15 to 16 perfect squares, right? Perfect cubes, we know a few of. 8 is a perfect cube. That's 2 cubed. 3 cubed is 27. 4 cubed? 64, very good. 5 cubed? 125. 6 cubed? 216. 7 cubed? I think I lost myself there. It's not 289, is it? No, that would be too small. 343. So the point is, you obviously don't need to know as many because they get bigger faster. Now I just have to see for myself. 7/3, 343 was right. And then I think I'm out of gas. I think I could do, wait, 8, 9. I mean, 10 cubed, you can do 10s. That's pretty easy, but 7, 8, 9, I don't know. I'll give you the, obviously, 10 cubed. You know the rule on 10s, right? Just if it's cubed, 3 zeros. If it's to the 5th power, 5 zeros. And I'm reviewing these only because obviously you're limited in your calculator use. So perfect squares, I'm not going to review, but perfect cubes, those are the ones that we should be expected to know. Fourth powers, I mean, you really just are going to two to the fourth is 16. 3 to the fourth, 81, very good. 4 to the fourth. 4 times 4 is 16, times 4 is 64. 64 times 4 is, what is it? I don't know. Maybe you don't have to know it. If I don't know it, you don't have to know it. 256. That is a familiar number, actually. 5 to the fourth, yes. Does anybody know it? Go ahead, Joe. Give it. I believe so. 5 to the fourth. Yep. And then we're out of gas. And 5th power is going to be even less. 2 to the 5th power, 32. 3 to the 5th power, is it 243? Well, let's think. 81 times 3. 243, right? I'm calling it a day there. That's the end of my road there. I'm out of gas. All right, so just some of the special numbers that you should just get used to seeing and being like, yeah, I'm pretty sure there's something there. So the 5th root of 32, obviously with 32, it is a perfect 5th power. The 5th root of 32 is 2. And the 5th root of x to the 5th is just x. No need for an absolute value there because it's an odd power. So you actually don't want an absolute value. You would be wrong. 4th root of 81, again, that works out perfectly. That's just 3. And then the 4th root of x to the 8th. Now, essentially, obviously when you're looking at exponents, you're kind of looking for 4 goes into that how many times? Twice, right? X squared. Now this is an interesting circumstance because it was an even root with an even power. So you would say we do need the absolute value sign around the x, but you're squaring it anyway. So isn't that going to make it positive anyway? So you don't need it here, but if you put it here, it would not be wrong. Okay? If you put it here, it would be wrong. If you put it here, it would not be wrong. It's just a little redundant. You're going to absolute value it, and then you're going to square it anyway, so it would have been positive anyway. So that's just redundancy. Okay? And then in radical 54, cubed root of 54, if we look at our cubes, 54 is not on our list, but what number does go into 54 evenly? 27. So we're going to split this up into the cubed root of 27 times the cubed root of 2. The cubed root of x we can't do much with. And the cubed root of y to the 9th is going to work out well because 3 goes into 9 3 times. So we can evaluate this with the whole number 3. We can evaluate this with y to the 3rd. And then these guys are kind of stranded ducks here, so they just sit underneath the cubed root in your final answer, 2x. Again, odd power, odd root. Don't worry about the absolute value sign. Okay? So again, review. One little added stipulation of PreCalc is kind of knowing that absolute value idea. You definitely did this last year. If you raise a base to a fraction exponent, the denominator is the root that you take, and the numerator is the power that your base is being brought to. And you should all be aware that this is fine as well. Correct? Okay? In fact, if you're evaluating without a calculator, I actually recommend this because I would rather you shrink the base first and then raise it to a power. That's just going to be easier to do mentally than raising it to the power first, getting a gigantic number, and then having to take the root of it. So for example, in this first example, 32 to the negative 4/5. The first thing I'm going to do is handle that negative exponent, so 32 to the positive 4/5. And then in my denominator, I'm going to make this, and here's where I'm going to elect to take the 5th root of 32 first, and then worry about raising it to the 4th power, because I think I'd be hard-pressed to find someone in here who, within a reasonable amount of time, if I did it in the opposite order, who could do 32 to the 4th power in their head in a reasonable amount of time. Nobody. So we first simplify that down to 2, and now we have our answer. So here's a new kind of skill as well. You never have had to do this without a calculator. Okay, and the next one, 25 to the 1/2 power is the same thing as the square root of 25, which is 5. X to the 4th to the 1/2 power, power to power you multiply, that's going to be x squared. And y to the 6th to the 1/2 power, power to power you multiply, 6 times a half is 3. So that's pretty straightforward. Last but not least, to the 1/9. So x to the 6th to the 1/9 power to power is x to the 6/9. We'll reduce that in a minute. Y to the 3rd to the 1/9 is y to the 3/9. And we reduce x to the 2/3, y to the 1/3. Now, with this, and with exponent rules in general, you have to kind of, if it says, pay attention to whether or not they want, if it's open response, the final answer in exponential form or radical form. So as we've left this right now, this is an exponential form. In a multiple choice, you're just going to have to look at the answers, and if that's not one of them and all of the answers contain radicals, we actually need to bring this back to a radical. So given, thank God, they both have a 3 as the denominator, we would make this the cubed root of x squared y. Okay, both of those are good final answers in simplest form. One's just in exponential form, one's in radical form. So if it's open response, pay attention to how they want it. If it's multiple choice, just whatever one's available. You have to be comfortable with that. Okie doke? Well, geez Louise. You want to start your homework? Yeah? I will project